Hello, AP Physics 1. It's time for us to continue our discussion of motion, and today we're going to talk about uniform circular motion. That's for objects going in a circle. So we've already discussed one-dimensional and two-dimensional motion, and now we're going to talk about circular motion, things going in a circle. Not necessarily going in a circle, things that are changing direction. That's the important thing. Whenever something changes direction, it requires a force towards the center of the arc. That's deadly important. They always ask this question on the AP exam. So, let's talk about the mechanics of something going in a circle or an arc or changing direction. So, the velocity of the object is always tangent to the pathway of the object. So, in this particular picture, the object is going around counterclockwise at this instant. When the dot is right here, the velocity is up and to the left. The acceleration, on the other hand, is towards the center. As long as it's going around and not speeding up or slowing down, the acceleration will only be towards the center, and that is called a centripetal acceleration. Remember that we have already talked about in one-dimensional motion over here that if an object speeds up, then the acceleration is in the direction of the object. And if it slows down, it's in the opposite direction. So we have two types of acceleration now. We have centripetal acceleration when the object is changing direction and it's turning. And then we have tangential acceleration, which is an acceleration where we speed up or slow down. So we can have both at the same time. In the example problems we're going to work later, you will see that, and I'll demonstrate that for you. We'll have a couple of examples. All right, so whenever you're changing direction, the centripetal acceleration is towards the center, A sub c, okay? Always towards the center of the pathway. We have a couple of ways to calculate that. The standard way is to find the velocity of the object, square it, divide by the radius of the arc that it's in. Now that we've talked about rotational motion already in class, there is also another way for us to find centripetal acceleration. It's omega squared r, where omega is the rotational velocity in radians per second squared. Well, sorry, it's in radians per second, and that omega is squared multiplied by the radius. So either one of these works great. It doesn't matter which one you want to use. How do we find this velocity in circular motion? If they don't give us the rotational velocity, in radians per second, how do we find this velocity here? Well, one way to do it is that the circular motion velocity when you're going in a circle, is the circumference divided by the time period, or 2 pi r divided by t, right here. T is the time period. Capital T is time period. And time period is equal to 1 divided by the frequency. So that's the rate at which it goes around in circles per second, or cycles per second, or revolutions per second. All right? So there we go. Next thing, whenever we're dealing with an object that's changing direction, you need to draw a free body diagram like we always do and identify the forces that are acting on the object. There must be some forces towards the center of the motion, or otherwise it wouldn't turn. So there's always going to be a net force towards the center of the arc. So build your F equals ma, except this time we're building it towards the center. That's why we have a C down here. So the sum of the forces towards the center equals ma towards the center. Now, that force towards the center could be friction. It could be tension. It could be normal force. It could be any other real force. Centripetal force is not a magical new force. It's just the name that we call the force or forces that cause something to turn in a circle. So never on a free body diagram, never ever draw a force and label it FC, centripetal force, because there's no such thing. The force will always be something that we've learned about already. Normal force, tension, spring force, gravity, something. All right, speaking of gravity, if gravity force is the force that's causing something to go in a circle. That's generally called an orbit. So like the moon goes around the earth because of gravity. The earth goes around the sun because of gravity. The earth-moon system goes around the sun because of gravity. All right, so if we plug gravity in as our centripetal force, because that's the real force, gravity is gmm over r squared. The big M is the thing that's being orbited. Little m is the thing that is in orbit, going around. And r is the radius of the orbit. And then on the other side of the equation, the MAC part of the equation, this m is the object that's in orbit. So this m is going to cancel, and it won't make any difference. And then we get v squared over r. That's our centripetal acceleration. And so the m cancels, one of these r's cancels, and that will leave us with the velocity of something going in a circular orbit will equal the square root of gm over r, where this is the mass of the thing that's being orbited, and this is the radius of the orbit. So the mass of the object in orbit is irrelevant. It doesn't matter. Everything in the same orbital radius around the same object will go the same exact velocity. If we substitute in what the velocity equals, which is this equation right here, circumference over time, then we get this. This is sometimes referred to as Kepler's law. I think it's his third law, if I remember correctly. It tells us the time period of something in orbit. So the time period of something in orbit is related to the mass of the thing being orbited and the radius of the orbit. Okay? We had to derive this on a test a while back. Now, one last thing, and I'm just dropping this in here because we're talking about gravity, is the acceleration caused by gravity near the surface of a planet is equal to g of the planet is equal to big G, universal gravitational constant, the mass of the planet, and the radius of the planet squared. Okay? So we'll work one of these in the sample problems we're going to do in a little bit, and we'll derive this in one of those problems, we'll derive this in one of those problems, and so we'll set all this stuff up, okay? We'll talk about this again, the acceleration caused by gravity, again when we get into forces, all right? And that's it. That's our basic structure for circular motion. The key thing to remember is when something changes direction, there must be a net force towards the center of the arc that it's going through, and the object is accelerating even if it's not changing speed. All right, thanks a lot. Have a great day. Bye.